So in this video, we're going to talk about orifice. So orifice, an opening with closed perimeter in a wall or partition. It is used for metering or controlling fluid flow. So in applications, may time na dapat ma-regulate natin yung lalabas o magdi-discharge na fluid sa tank natin. Closed pipe and a reservoir with multiple partitions. So by using orifice, pwede natin ma-regulate yung flow rate or discharge ng flow dun sa opening. Orifices are classified or distinguished by its shape. They are circular, triangular, or rectangular. Also, orifice can be classified by their form of their upstream edge, which has a round upstream edge or a sharp upstream edge. So, in round upstream edge, it is in contact with the fluids and also with the fluid's energy head. While in sharp upstream edge, it is really pointed, not unlike the round upstream edge. So now let's move on to a sample problem. So in this problem, we're going to solve about fluid flow measurements in constant head orifice, which in condition it is in steady flow. Determine the discharge at the orifice from the figure shown. So as you can see in the figure, there is a reservoir. This is a tank filled with water. So the tank is under pressure, or there is an input air pressure or gauge pressure of 40 kilopascals. So the head of the water from the orifice situated below the tank up to the liquid surface is 3 meters. Assuming that this head is constant and that there is a continuous supply here in the tank. So the required is to determine the flow rate or Q. So why I wrote Q sub A rather than Q sub T? It is because C is already given. So if C is not given, then we can compute for Q sub A or actual discharge. We can only compute for Q sub T or theoretical discharge. Also, if HL or the head loss is given, so the system would be in an ideal, then the computed discharge on that particular equation be Q sub A. So if the system is ideal, then we can compute for Q sub T. So our solution, so we only use one solution. We can also use Bernoulli's energy equation, or we can use the derived formula. So our derived formula is Q sub A, or the actual discharge, is equal to C, or the coefficient of discharge, times A sub O, or the cross-sectional area of the opening of the orifice, times the square root of 2G uppercase H. Remember that the value of uppercase H depends on the existing energy that will trigger the discharge at the orifice. So in this case, H comprises of the following: a pressure, the input gauge pressure at the tank, that's P over gamma, plus head, which is 3, or lowercase h. So as you can see, there is no velocity of approach as you can see in the figure, so we neglect the velocity of approach. Then we input the given values, which has a pressure of 40 kilopascal over 9.81 kilonewton per cubic meter, which is the specific weight of the water, plus 3 meters. Now, solving it in the calculator, we now have a value of uppercase H, which is now 7.0774 meters. Now we have the value of the head of the water, so we can now easily input the given values into the equation. So we have a 0.92 for coefficient of discharge times the cross-sectional area, which is pi times 0.05, which is the diameter square rate over 4 times the square root of 2 times the gravity, which is 9.81 meter per second, times the head of the water that we got earlier. We can now easily input the given values into the calculator, and we have a actual discharge of 0.0213 cubic meters per seconds.